right, we're finally ready to work on finding limits algebraically. And this is going to be a big one for us. It's really important to understand the other methods as well, but this one is a little more work and you'll want to give it some extra attention. It also lines up a lot with what we need limits for when we're finding derivatives. So pay close attention to directions. If the directions say find the limit algebraically and you go about finding it numerically or graphically on a test, that's going to get you in trouble. So I do want to be able to ask you to do specific methods and see that you understand all three of them. When you're finding limits algebraically, I'd still start with seeing if you even need to do much of any work. If your function happens to be continuous at the value that you're interested in, you can just plug that in and you're done. Here's a really good example of a function that is not continuous at our value. At x equals 2, this function has a 0 in the denominator. So definitely we can't just plug in and evaluate the function to evaluate the limit. An interesting next question is the numerator also 0 or not? And in this case it is. 2 squared minus 4 is also 0. So this is a 0 over 0 limit, which is an indeterminate form. And again, those are important. Those are the ones that we often can simplify algebraically and get a nice answer because they're often removable discontinuities, just one little hole in the graph. And if all you have is a hole in the graph, you should have a nice value for your limit. The limit doesn't care about the hole, just nearby. The algebra we're going to use is the same algebra that we use for our difference quotients. These are not difference quotients. These are not slopes. This is just a question about y values, but we can use the same algebra. Please use your limit notation carefully. I'll be looking for that. Don't just scratch out your algebra and not write the limit and then write your answer. This is one place where I am going to be picky about your notation. Here, for a quadratic, we can go straight to factoring. X squared minus 4 is the same as x plus 2, x minus 2. And that's all divided by x minus 2, so I can cancel. And I get the limit as x approaches 2 of x plus 2. And notice that the x minus 2 that canceled was the exact thing that was giving me the 0. That was the exact thing causing the problem. Also notice that if I hadn't written the limit, I would be lying to you. It's not true that this first fraction right here is equal to x plus 2. It mostly is true that they're the same, but it's not true when x equals 2. So we would not be correct to say that those two are equal unless we tacked on an x cannot equal 2 on the right-hand side. However, with the limit, we are saying something true because the limit doesn't care what's happening right at x equals 2. It only cares nearby. So that hole in the graph doesn't matter at all. And we can go ahead now that we've removed the discontinuity and say, well, when x approaches 2, we get 2 plus 2, which is 4. So basically we have a function that looks exactly like the line y equals x plus 2. But it has a hole in the graph at, what was it, 2, 4? And if we ignore that hole, we can easily find the value of the limit. So that's what we're really doing there. All right, let's try another one. This time we're interested in what happens as w approaches -1. On the top, if I plug in -1, I get -2 plus 1, which is -1. On the bottom, if I plug in -1, I get 1 minus 3 plus 2. I get 0. So this, I definitely can't just plug in and get the answer. This is going to be a little bit different situation than the last one, in that I now don't expect to have a removable discontinuity. I expect to have a vertical asymptote. And if it's a vertical asymptote, you're not going to get a nice algebraic simplification. You're not going to get a particularly nice answer. You're going to get does not exist or plus or minus infinity. But let's play around a little bit just to see. You might not notice that right away. This is factorable. So if you're not really paying attention, you might go ahead and factor it. Fantastic, but you should see pretty quickly that you can't cancel, so it's not helpful. So we don't have an algebraic solution. and that can happen, and it's okay to just say that as your answer. I can't figure this out algebraically. I'm going to jump to numerical or graphical methods. Here, I need to plug in numbers really, really close to -1 to see if I'm getting plus or minus infinity, or I need to check a graph. And I've already got this one typed in. I don't have a very nice window, but I'll move it around a little bit. We were interested in what was happening when x was near -1. Okay, so there it is, our asymptotic behavior. And we can even, if you'd like to, type in x equals -1 so that we can see that asymptote. And what it looks like is that on both sides, my y values head to -infinity. So in this case, the limit does exist, but it is -infinity. If you happen to get a function where on the two sides of the asymptote, the y values head to positive infinity and -infinity, that's going to be a does not exist automatically. Unless they both go up or both go down, you're going to end up with a does not exist. But here it is okay to say, well, this one, both sides went to -infinity, so that's going to be my limit. Okay, just one more like this, and then we'll split and make a new video. How about the limit as k approaches 4 of k squared minus 23 over k squared minus 2? And again, this is a pay attention lesson. If I just start trying to crunch through, I'm going to be a little concerned because k squared minus 23 doesn't factor nicely. But if I remember to check in advance and see if I'm even in an indeterminate form, I get 16 minus 23 over 4 minus 2, which is not a 0 over 0. In fact, it doesn't even have 0 in the denominator. So there is no discontinuity at k equals 4, which means we can just plug the number in and do the arithmetic and we'll have our answer. So I think I'm seeing -7 over 2 for that one, and you're all done. So even if the directions say algebraically, if you could just do that by plugging in the exact value, you're done. Those are fantastic.